So one of the most important concepts to understand in statistics is the relationship between samples and what is going on in the greater population at large. And one of the things that we use to investigate making conjectures about the population at large is through samples. And so what we're going to look at next is what's referred to as a sampling distribution. So a sampling distribution, if you look at this sort of bottom paragraph here, different random samples yield different statistics. So remember what we said about samples, and that when you take a sample from a population, there's variability that's involved. So if you take a sample from a population, there's no guarantee that if you did the exact same sample size and did the sample over again, that you would get the same results. So a sampling distribution essentially is where you sample and you come up with all possible samples from a sample. So with some different things with samples and populations, one of the things that we do is we collect samples from the population, and what we're hoping is that if we do it properly, that the results that we get from the sample will be representative of the population at large, and if it is, then we can make accurate inferences, accurate predictions about what is sort of happening within the population. So some terminology that's involved with sampling and population, and one of which has to do with what's called a parameter. So a parameter is some sort of number or value that describes some characteristic of the population. In statistical practice, the value of the parameter is usually not known. So if you recall back to what we did in class with the German tank problem, the parameter of that problem was the number of tanks that the Germans had, and when we were working through that problem, we did not know what that exact value was. That was the parameter of interest. A statistic, however, is a number that describes some characteristic of the sample. The value of a statistic can be computed directly from the sample data. So that was the value that you got when your group created the formula for the German tank problem. The statistic that you got was the value that you computed from the formula that you created. And we often use a statistic to estimate an unknown parameter. So we're basically trying to take some sort of unknown value in the population. We're trying to collect a sample, and the sample that we collect and the number that we get from that is called a statistic. So in terms of just some different things to sort of try to keep this straight in your head, just remember that statistics come from samples, parameters come from population. So, statistics and samples both begin with S's, parameters and populations both begin with P's. So hopefully that helps you to sort of keep those two terms sort of straight in your head. So when we're talking about some different things as far as variables go, we write the Greek letter mu for the population mean, and we write x bar for the sample mean. So that's when we're talking about quantitative data. And if we're talking about categorical data, we use p to represent a population proportion, and we use p hat to represent the sample proportion, and that's when we're talking about categorical data. So an example of what we're looking at here, and this just basically deals with some things from a terminology standpoint, and the question says to identify the population, the parameter, the sample, and the statistic. So just remember that your population and your parameter are both linked together, as well as the sample and the statistic. So the population is the population of interest, the parameter is the value that comes from that population of interest, the sample is what it is that we're sampling, and the statistic is the value that comes from that sample. So in terms of the question here, it says the Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So the population here, and this is all the different people that could have been a part of the sample, the population here is all U.S. adults. So within that population, they asked 515 of them. So the parameter of interest here, what it is that the reason that we're sampling is we want to know what's the proportion of all U.S. adults who believe in ghosts. That's what we don't know about the population and what we would like to gain some sort of information about. The sample in this case would be the 515 people who were interviewed, And the statistic that you get from the sample is the results here. So they said that of their 515 U.S. adults, 160 said yes. So the proportion of those that said they believe in ghosts would be 160 over 515, which is roughly about 0.31. That's the proportion of the sample who say they believe in ghosts. That 0.31 is the value of the statistic. So the population and the sample is what we're talking about. The parameter and the statistic represents the values that we're trying to figure out and then what we got from our samples as a result. So Part B says, during the winter months, the temperatures outside the Starnes' cabin in Colorado stay well above freezing, 32 degrees Fahrenheit or 0 degrees Celsius, for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times during the day, and the minimum reading that they get is 38 degrees Fahrenheit. So once again, I want to know what's the population, what's the parameter, what's the sample, what's the statistic for this. So the population here is all of the times during the day that are in question, because they're not going to measure all of the times, but that's the parameter of interest in this case. So in this case, what we're looking for in terms of the parameter of interest, it's the minimum temperature in the cabin for the day, because she wants to know how low will the temperature get based on the thermostat being set at 50 degrees. The sample, in this case, is the 20 different temperature readings that they take, and the statistic for this ends up being what the sample minimum was, which in this case, of the 20 samples that they took, the minimum reading was 38 degrees Fahrenheit. That's the value of the statistic. So that's just some different things with some terminology involved with parameters and statistics. So some more sort of questions involving that. And what I have here is two numbers that are in bold. So for this first question here are the two numbers that are bolded. And it says, on Tuesdays, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contain, on average, 19.6 ounces of iced tea. So what we're looking for here is each boldface number in the question is the value of either a parameter or a statistic, and we want to know which of those two is it, and then we also want to use proper notation to describe the number. So proper notation is, we're basically talking about mu and x bar if we're talking about quantitative data, and p and p hat if we're talking about categorical data. So in this case, because the data is quantitative, we got a 20 and a 19.6, we would basically be talking about mu and x bar here in terms of using appropriate notation for this. So the parameter here would be the 20 ounces of iced tea. That's what the bottles were supposed to contain. However, when they did their sample, the statistic for this was 19.6. So just notice that this value refers to the population at large. So I'm using mu to represent that, and then this was the value of the statistic. So I'm using x bar to represent that right there. So just once again, remember, I'm using mu and x bar because the data that we collected, the samples that we collected our data with were quantitative data. For question number 2, it says, on a New York to Denver flight, 8% of the 125 passengers were selected for random security screening before boarding. According to the Transportation Security Administration, 10% of the passengers at this airport are chosen for random screening. So once again, if we're talking about what type of data we're using here, so in this case, this is an example of data, because we're talking percents here, this would be categorical data. And if we're talking about using proper notation here, the parameter of interest would be the 0.1 or the 10% of passengers, okay, that are supposed to be chosen at the airport. The statistic here represents what the sample was that was taken on the flight from New York to Denver. So just once again, note here, the parameter, because we're talking about categorical data, if we're using appropriate notation for parameter, I'm going to use the value of p, and for the statistic, I'm going to use p hat. So just keep in mind that whenever you're doing parameters and statistics and talking notation, just make sure that you're using your appropriate notations here. So that's mu and x bar when we're talking about questions like this that involve quantitative data, and that's P and P hat for questions like this when we're talking about data that's categorical. So some other things that are involved with samples, and it has to do with some different things involving variability. So just remember that when you're talking about taking samples from a population, even if those samples are of the same size, and what this illustrates here is you're taking samples from a population, and if we assume that those samples are of the same size each time, remember that there's always variability that's involved in your samples. So, and by that what we mean is that if you take a sample from a population and then you take another sample of the exact same size, there's no guarantee that the results that you get will be the same as your original results, and in fact in most cases they won't be. So, and also just remember that the reason we're taking samples in this case is because we usually have a population value that's unknown. So we're trying to take some samples from that population to see if we can discover some sort of unknown value about the population. So that kind of leads us to the concept of what's called a sampling distribution. So a sampling distribution, simply put, is the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Meaning that if you were to take a random sample from the population, a sampling distribution would be sampling, and the results that you get would be as if you took all the different possible samples that you could from the population. So to give you sort of a for instance with this, one of the things that we'll look at is, and we'll use this as a small sample size. So let's just say, for instance, we were going to take a sample of, let's say, 4 people, and we'll just sort of label these people as A, B, C, and D. And what if what I wanted to know was what was the average height of somebody that was in this population? So if I took a sample size of 4 people from this population, what I would be looking for is all the different ways that I could sample, all the different ways I could create samples from this population of 4 people. So let's just say I was going to use my sample size of 2. So one of the samples that I could choose from this population of 4 people is I could choose person A and person B, and I could figure out what their heights were, or what their average heights were. That would be one possible sample. Another possible sample would be I could choose person A and person C. That would be a different sample. I could also choose person A and person D. That would be another possible sample. I could also choose person B and person C. That would be another possible sample. Then I could choose person B and person D. That would be another possible sample. And then finally I could choose person C and person D. So if I had a population of 4 people and I was going to choose 2 people at random from that population, what I would have here is a total of 6 different samples that I could take from that population. So this right here, or these values that I would get from these 6 samples, this would be what is referred to as a sampling distribution. And basically it's the results that you would get if you took all possible samples from the population. Now when you get a population size that's rather large, and certainly much larger than 4 people in this case, one of the things that it becomes hard to do is to compute what is a sampling distribution. So one of the things that we use, one of the things that we do to find what a sampling distribution would look like when a population is large is we use simulations. And that's one of the things that we will look at in the next lesson here. And that has to do with some different things that are involved with sampling distributions and what those values look like with some of the different graphs that we have. So if you take a look at this right here, and what we're going to basically kind of go through here is that the concept of simulation. So one of the things that we'll do with your calculators is we'll take some different samples from some populations with a given value that comes from your sample, and we'll look at what some different sampling distributions would look like based on some of those different factors.